Hello all dear friends, let's see this very good problem of current electricity from Pathfinder. It's a MCQ question number 24-25 based on a paragraph. So let me explain the setup of this question. So these are the two conducting concentric shells, radius r and 3r. Initially they were uncharged. And there is a point charge q between them, capital Q between them at a distance 2r from their common center. Some setup is being made. So a conducting wire goes from the inner shell uh, outside the system without touching. This is shown. Actually there is no electrical contact, so we can show something like this. So without touching, it goes outside, and we want to create some electrical contact between outer shell and inner shell through this R1, and there is S1. When S1 is closed, electrical contact will be made between the inner shell and the outer shell. In the same way, to create electrical contact between the outer shell and the ground, resistor R2 is there and there is a switch S2. So when switch S2 is closed, so electrical contact between outer shell and the ground will be established. So now two things is asked. First thing is that S1 is closed and S2 is open, and let S2 be closed for a long time so that a steady state established, mean a steady charge appear at the both inner surface and the outer surface of the shells. And then how much is the total heat developed in this resistance R1? That is the question number 24. The question number 25 for this asks, steady state between here is established, and now S1 being closed, it was closed, it is let it be closed, and before S2 was open, now S2 is also closed. After S2 is closed, and another steady state let establish, and then after closing S2, how much more heat is dissipated? These are the two questions asked. So let's try to get the answer of the question 1. So that is the picture. So before steady, suppose we close it here, this is closed, and some charge flows between these two. S2 is open. At a general moment, before a steady state is not obtained, so before, at a general moment, I am talking about at a general moment before steady state, charge distribution would have happened. So because of the potential difference, suppose the new charge on the inner shell is a q. Out of the q, the inner surface will have a 0 charge and this will have a charge q. One more thing we should understand. Okay, let me explain just this thing. The charge that will be here will again be divided into inner and outer. The inner part is very clear. So this is q, this is 0, and this is capital Q. If I take the outer shell, obviously it will have some thickness. So if I take any Gaussian surface within the interior of the outer shell, net flux is 0 because net electric field is 0. So net charge enclosed would be 0. So within this, net charge enclosed should be 0. So the charge here would be, because a charge q is there and the charge capital Q is there, so the charge here would be minus of small q plus capital Q. So that is one thing. So charge at the inner surface of the outer shell, here that should be minus q plus capital Q. And now one thing, total initial charge of these two is 0. No part of this charge is going here. Because of the electrical contact being made through S1, the charge can flow this part, but no charge will remain here. Whatever charge flows, that can go here or it can go here. So still the total charge of the shell 1 and shell 2 will be 0. So to make total charge 0, this is q, this is minus q, this is minus q. So here at the outer surface, a charge plus q should appear, and that may change. That may change means this q may change. Outer surface charge will be immediately fixed. So when the steady state will happen, so we will find the how much is the that Q. Now at a general moment right now here, suppose potential of this shell is 1. So the potential of this point up to this point connecting, there is a potential V1, and potential of shell 2 is say V2. So potential at this point is also V2. First I want to calculate V1 and V2. So V1, potential of shell 1. Before calculating, we should also get know whether the charge distribution is uniform or not uniform. So look at this charge distribution. This charge distribution is non-uniform because of the presence of this capital Q charge. So this is a non-uniform distribution. Same way, because of this distribution will also be non-uniform. And we know that because of the through the advanced property of the conductor, shielding effect, so whatever charge are within the shells, they have no effect in the distribution of the charge at the outer shell. This distribution can only be changed because of the some outer charge, and there is no charge outside the shell too. So this distribution will be distribute such that surface charge density at any point is inversely proportional to its radius of curvature, and it is a shell. So its radius of curvature everywhere is equal to its radius. So this distribution will be uniform. Now potential of the shell 1. The potential of the shell 1, there is no electric field inside. So whatever is the potential at the surface, that is the potential at the center. So basically potential of the shell 1 is nothing but its potential at center, because of all charges, because of its own charge and also charges outside it. So benefit of writing potential at O is because these charges are not uniform, but because these charges are at a same distance from O, so we can directly write potential KQ total by R. So because of this charge, potential is how much? K, I can write it here. K I will take outside, Q by R. Because of this capital Q charge, which is at a distance 2R, K capital Q by 2R. And these charges I can write potential at once. The total of this is minus Q. So because of these two, the potential is minus Q by 3R. So potential of shell, inner shell, when the charge here is Q, so this just simplify this K, and that will be Q by 2R plus capital Q by, this is not 2R, that will be 2Q by 3R, and that will be Q by 2R. Equation 1. And potential of shell 2, there is going to be some problem, but there is a way. If I want to write potential by each part, because of this one I cannot write potential here because this is a non-uniformly distributed. Because of this I can write at this point, at some other point. Because of this part I cannot write potential because these are the non-uniform. Because of this part I can write, but there is a way. See, what is potential at a point? Potential is basically integration of minus E dot dr from infinity to that point where I want to find the potential. So I need electric field. So if I go from here to here, this electric field is complicated. I don't know about the electric field, so that way I cannot get potential from here to here. So but I can go from infinity and come up to here. If I come from infinity and reach up to the outer surface of the outer shell, so I will encounter an outside electric field, and that outside electric field will only depend on this charge, because of the property of the conductor. the inner shell, the total, the charges at the inner surface, the total electric field because of the charges at the inner surface have a net electric field 0 at outside point. So because of all these charges, net electric field outside is 0. So net electric field outside is because of this charge only. So because of this charge, if I come here, maybe at a distance, general distance r dash, that will be electric field kq dash by r square. So because of this electric field, potential here will be normal way. If you integrate, that will be kq, k capital Q divided by this radius. So that directly we can write that potential of the shell 2. So that way we can write potential of shell 2. So potential of shell 2 is kq divided by, what is the radius, 3r. Second equation. And I want to write the potential difference. Suppose the this current flows something like this. So this is higher and this is lower. So this is plus and this is minus. So what will happen? So I just want to write potential difference between shell 1 and shell 2. So let V is the PD between shell 1 and shell 2. So V would be how much? V1 minus V2. So V1 minus V2, if I just make a difference of these two, 2Q by 3R and Q by 2R, so that will be K into 2Q by 3R, and if I difference of this would be simply capital Q 1 by 2 minus 1 by, that will be 1 by 6 by 6R. That is one thing. Now let's go to next page. So potential difference we obtained, V is equal to K. Here I can take a 6R outside, K by 6R, and it will be 4Q plus capital Q. So when at at the steady state, when the charge flow will stop, so at a steady state, this potential difference that was there, that potential difference will be 0. At steady state, this potential difference 0. Just if I equate it, so I will get Q will be how much? Minus Q by 4. Now see, initial charge here, initially this charge was 0, this charge was 0, initially it was uncharged, 0 0, and this charge would be obviously minus Q and capital Q. But at a steady state, when the steady state has established, so this charge has become how much? This charge, this will be 0, and this I've just got minus Q by 4. So that will be how much? Minus Q by 4, that will be capital Q. So this will be minus 3Q by 4. So from here, from this distribution to this distribution, how much total heat has dissipated? And you can see that from the initial charge 0 to becoming minus Q by 4. So obviously the current would have been flowing like that. So a current is flowing like this current is flowing, and the potential difference V is there. This is a V1 and V2 in between. So I want to find the heat dissipation in that resistor R1. So for that, let me write the power dissipation. For the power dissipation, I can write I square R, I can write VI, I can write V square by R. And remember one thing, if it is as the total heat dissipated, there is no role of the R1. R1 has only role in increasing the rate of heat dissipation or slowing the heat dissipation. If R1 is more, so the rate of dissipation would be more. If R1 is less, it will be less. The more the R1, the fast. Sorry, if the R1 is more, there will be a gradual way the heat dissipation. If R1 is less, it will be faster way. So it will basically impede the heat dissipation. Total heat dissipation, there is no role of R1. You will see. So for the power dissipation, I am using this formula VI. So V is the potential difference and I is how much? I is the dq by dt. And P is dH by dt. So that is a V dq by dt. So dH is equal to V dq. And what is dq? dq is the charge that is flowing. At a general moment, the charge here was that small q. The initial value of this q is 0 and the final value of q is minus q by 4. So let me go to the next page. So dH is equal to V dq. As a function of q, I have this potential difference. So I am writing here. So this V is equal to K by 6R 4Q plus capital Q dq. Integrated to get the total heat dissipation. This I don't want the diagram right now. All right. So this integrated, that is Q by 6R 4Q plus capital Q and dq, and that integration will go from 0 to minus q by 4. So K by 6R, the integration of this thing will be 2q square 4q square by 2, and that integration will be capital Q into small q, 0 to minus q by 4. K, I am writing the whole value of K, 1 over 4 pi epsilon naught 1 by 6R, that will be 2q square 16 by that will 16, so that will become 8, and this will become minus q square by 4. So multiply by 2, multiply by 2. So finally I will get q square. This is 4, this is 6, and from here 8 pi epsilon naught r. So how much that will be? That will be 24 into 8, 192. So the answer I will get q square divided by 192 pi epsilon naught r. That is the heat dissipation in R1 till steady state. Let's see. So that is option C. And now what happened? The steady state is established here. So the charge is 0 minus q by 4, 3q by 4 and q. They've come to steady state and the charge flow has stopped. S1 is closed, S2 was open. Now what we want to do? We want to close S2 also. So see, already this steady state is established, no charge is there. If you do anything here, like this condition was this condition is because of the equality of the potential. If you increase this charge by any amount or decrease by any amount, basically if you change this charge by any amount, what will happen? The potential of the both shell will change by the same amount, so there will not be any change in the potential difference. So now whether this charge goes or remain, the inner charges are not going to change. If this charge is not changing, so there is no current in the shell. So now if the S2 is closed or open, what will be the effect of S2 open or closed? The outer shell charge may change. If this charge changes, I am telling you, whether this charge remain constant or does not remain constant or changes. It will not have any effect on these charges, because if it changes, it will change the potential of both shell by the same amount. So still the potential difference 0 that was arrived, so it will be there. And this charge was because of the same potential difference, 0 potential difference. So this charge is not going to change. If this charge is not going to change, so there will not be any current here. So now if I close this shell, this switch, so only charge that can change is this charge. So there is a potential difference between this and this potential is 0, and it has initially just at the moment of closing potential. So the charge Q will eventually go to ground. It will take time, theoretically infinite time, but it will go. If the R2 is less, if I just connect by a conducting wire, it will be immediately go. If the more R2, the slower it will go, but eventually it will go. So finally, eventually this charge will become 0. So that will be the final steady state. So basically I have to tell what is the extra heat flows, extra heat dissipated after closing S2. The same way, the power dissipation in this R2, I will write P R2 is equal to a potential difference from here to here. Suppose this potential obviously is 0 and this potential is say V. So that would be how much? V into that I. V into I. And suppose now let me write another variable. Suppose at a general moment when this charge is flowing from here to here, at a general moment, suppose this charge is a Q dash. So potential of the outer shell would be simply a K Q dash by 3R, and I will be how much? That dQ dash by dt. This Q dash is decreasing, so I will write a minus sign, and this P2 would be dH2 by dt. So dH2 by dt would be how much? Minus K Q dash dQ dash dt by 3R and dt. So dt will get cancelled. So dH2 would be minus K Q dash dQ dash by 3R. So total heat dissipated now, delta H2 would be minus K by 3R, take outside, Q dash dQ dash. Initial Q dash was capital Q, and when the all charge will go to the ground, the Q dash will become 0. So that will go from uh, capital Q to 0. So this integration would be K by 3R and Q square by 2. Let's put the value, go to next page. Delta H2 is equal to 1 upon 4 pi epsilon naught one by 3 and 1 by 2 Q square by R. So that will be Q square by 24 pi epsilon naught R. Let me check the answers. So see, options. How much total heat is dissipated after the switch S2 is closed? Until new, after the switch S2 is closed. So heat dissipated in there is no extra heat dissipated in R1. So this is wrong. This is wrong because it is written that heat is dissipated in R1. Heat dissipated in R2 is Q square by 24 pi epsilon R, and no heat dissipated in R. That is correct. Both the resistors dissipate different amounts of heat, total amount of which is, that is wrong. They are only the R2 is dissipating it. So that is the answer to both of the questions. Thank you. It was indeed very good question.